applications of chapters, what was the information we learned in the previous chapters. And chapter 4 is basically energy analysis. On closed systems. So a closed system means what? No mass across the boundary, right? We can have heat, we can have other forms of energy, just no mass across the boundary. Closed system. No mass flow / exchange. Across the system boundary. So here I have some system, right? I have some container wall, which I put in red. And I could say, put an M here, I could have a Q here. The system has the temperature, pressure, and volume associated with it, right? Closed system. No. Of course, I draw my cartoon of my system, and I have a boundary. Focuses on the work done, and heat transfer. So here's my boundary, here's my system, and we're looking at energy analysis on a closed system. So we don't have mass flow, but the system size can change, or system volume can change. Plus there are changes in pressure, temperature, enthalpy, internal energy, and entropy. So remember H, right, enthalpy, H is equal to U plus PV. So the system size or volume can change, plus you have changes in temperature, pressure, and volume, right? And so if you have changes in temperature and pressure, then you have to have changes in enthalpy, internal energy, and entropy, because these are state functions, and I can define them by these two. So if the system size changes, what happens to the boundary? It moves, right? So it changes. So I keep on focusing on, you need to identify the boundary, right? You can draw all the pictures you want, but if you forget about the boundary, you haven't done anything. Just like if you're solving a differential equation, if you don't apply boundary conditions, you cannot get a solution. You just get some expression with a number of, I guess an infinite number of possibilities. But until you define the boundary conditions, then you can get an answer. It's just like if you're doing thermodynamics, you can define your system, you can define the problem, but if you don't identify a boundary between your system and your surroundings, you cannot get an exact answer. Okay, so related to this, work, W, right? And then I can do it like dW equals F dx. Okay, physics. So that's just the physics way of doing it. And we deal with not forces, right? In thermodynamics, we do deal with forces, but we're not really looking at forces. We're looking at making more forces per unit area pressure. So we deal with pressure, volume, temperature, and enthalpy. So pressure, force per unit area. So let's draw a little cartoon man. And he's in a box. Okay. And there's a boundary. That separates him from the surroundings. I could put the boundary above this top. So if I put some force on this, I could put a positive force or a negative force. This has some cross-sectional area. And the pressure is related to the force. You know, if F plus just means that it's a negative pressure on my stick man in the box. Force equals pressure times area. We write it like that. And then in this case, considering force by the system. Force by the system. So who is this? What is the system? My stick man in a box, right? You could apply pressure up, right? You could lift, or you could pull down. I could say, I could reverse it around and not look at him directly as, and I could say the pressure related to the surroundings, and of course there's a sign convention associated with that. But I've chosen F like this to match up with the work by the system, right? That we've used earlier. So in this case, I can go back to my dW, and I have pressure times area times delta X, and dV is equal to A times dx. So I get work is equal to P dV. This is work by the system, right? F plus force by system, F minus force on the system. Now I could change things around and not have a different sign convention and things would change, right? But there's a directionality associated with the work done or work by. So we're just taking this the same way. So we have the similar integral, negative integral, right? So integral from 1 to 2 dW equals the integral from state 1 to state 2 P dV, work by the system. Work by the stick man. If you notice, I started with F considering force by the system. I did all this, and I have no minus sign here. This work by the system. Now, the way we've written out the first law in definition, we said we put a minus W, right? So we were looking at work on the system. So that just ends up being the integral from state 1 to state 2 minus P. And I could put my subscripts, work by, same sign convention as we had earlier. I just used the stick man analogy with the pressure to kind of combine this whole idea of a control volume, and thermodynamics deals with control volume, changes in pressure, temperature, internal energy, and whatnot, and we have a moving boundary. So this might not be a stickman, it might be our new Volkswagen engine, or they're defying emissions, but anyways, nevertheless. So they tried to fudge the numbers to get the emissions right.
All the auto manufacturers.
Probably. Probably.
Have they fooled them like for 7 years?
7 years. At some point you get caught. Area, total network area, and PV diagram. For pressure. Okay, pressure P1, P2. I got path A, path B. So I'm just gonna put a red line, make A red, and then make B red. Anyways, but I have some path, right, from state 1 to state 2. State 2 has a corresponding temperature and pressure. I'm only listing the pressure here, but I'm at a given volume at state 2. My system, right? Closed volume, right? Volume 2 is less than volume 1, so this is kind of the stick man where the cylinder or the roof falls down. And so the net area within here is the total or net work for the process. So I start at state 1, I go to state 2, I come back to state 1, closed loop, it's a cycle. The net work done in this process, cycle type process. I could have the net work done for a process, but the process just might be from 1 to 2, then it would be the area under this. Or I could have the network done from going from 2 to 1, and then it would be the area, everything under there. So let's consider something where the network done can be calculated easy. So let's just not have some funky curvature to our paths. And in this case, I start at state 1. I go to state 1A, then I go to state 2, then I go to state 2, I call it 2B. So I have a path 1 to 1A, I got a path 1A to 2, I got a path 2 to 2B, and I got a path 2B to 1. So let's just, what is this? Network done on or by? On? Okay, so let's just say we don't know, and let's just consider that the area represents, right, the work done by the system. Okay? I already gave the clock analogy, right? But let's say we don't know, and then we'll guess that it's that. So the work done net by the system has to equal P dV. I don't have a minus sign because I'm saying net is by. So I don't have a minus sign here. So then when I do that, I have work net, work by, path 1 to 2, plus the work by from 2 to 1. Okay, so the reason why I just went from 1 to 2 and 2 to 1, I can really break this up into each individual path, but from going to here, I have no area, right? And from going here to here, I have no area. So work.net is equal to the integral path A 1 to 2 PV plus the integral from 2 to 1 PV taking path B 2 to 1. So I just wrote it again. Called path A, path B. Path A, work by for path A is the integral from 1 to 2 d work by, put a subscript A, which equals the integral p dv 2. Here I have the same type of thing. 1 to 1a p dv plus the integral 1a to 2 p dv. And this term here from 1 to 1a is 0. And then this one here, pressure is constant, it stays at P2. So this whole integral just ends up being P2, and then V2 is greater than V1, so I have V2 minus V1. So work from going to here to there is equal to P2, V2, yes. So in this case, no change in volume at constant pressure. Or not constant pressure. No change in volume. No area. And then here I have a change in volume. At constant pressure. Okay, so I just got the area under this curve, which is basically everything down here, and then I need to do work by from path B. So in that case, I got the integral from 2 to 1 p dv, which equals the integral from 2 to 2b p dv plus the integral from 2b to 1 p dv, which just ends up equaling, right? There's nothing there, there's no area from here to here. So it's just this part. This one's 0. So equals the integral from V2 to V1 P V. And the pressure is P1. So just do this. P1 is constant. So we got P1 V1 minus V2. I can switch this around, right? P1 minus V2 minus V1. So if I do the net, P2 V2 minus V1 minus P1. Okay, let's just get to the final answer because it's just P2 minus P1, V2 minus V1, height times width, double cube, right? Anyways, I just did a really long-winded way of calculus for calculating the area of a square. But the whole point is that you want, even though it's that, you know, we want to write out an integral form because it's very rare that you have areas in thermodynamic processes that just are cubes. Although you'll try to make something behave so you get an area like a cube. You'll try to engineer it so it follows that, because then you're making some process isobaric, right? Or no change in pressure in another one, right? Or I guess it's the same thing, but nevertheless, here I have, it was just talking about the sign change, but I already did the sign change here. So if we assume the wrong thing and we ended up getting a negative area, right, then we would know that it was actually work on the system. But we did it the right way. Clock. So if I have my clock going like this, we had this clockwise, right? It's a clockwise cycle. Put my hand up it does work on me, right? It moves my hand, the clock does work on my hand. So the area represents, when it's like this, work by the system. However, if I were to, I'd have to do work on the clock to make it go the other way. So let's just talk a little bit more about this. So I guess I already said it in words. This last example, right, represents the boundary. Work done in a cycle of a closed system. Where the cycle could be broken down into two main processes. One process of constant pressure and another one of constant volume. So there's a lot of other processes. So there's such thing as a polyotropic process. And in that case, there's a relationship between the pressure and volume, where PV to the nth power equals a constant. There's an isothermal process, temperature equals a constant. Then we have an adiabatic process, Q equals 0, no heat transfer. And then there's a new type of process called an isentropic process, and this is where delta S equals 0, so that means no change in entropy. So kind of the say-all of all processes that you're going to try to engineer at some point within some engineering cycle is to try to make at least somewhere within your cycle a process that is isentropic. Right? Next best thing. So isentropic, if you remember the integral, right? We had this dq over t. So isentropic delta S equals 0 and adiabatic delta Q is equal to 0. So the next best thing is to try in some part, so we have this 4-step process in our cube. So the next best thing is kind of make some part of your engineering process try to make it adiabatic where you have no heat exchange. You might want a lot of heat exchange in other parts, but you're going to probably need some part where it's adiabatic. So let's just go back to this one here. So I have PV to the nth power equals a constant. So I can have P1, V1 to the n. Since it's equal to a constant, then P2, V2, it equals P2, V to the n. A special case, n equals 1. So I have P1, V1 equals P2, V2. Ideal gas, PV equals m times the gas constant times T. N equals 1. That means this is equal to a constant. If this is equal to a constant, so I'll just put T comma, M comma, RG comma, equals a constant. So we're looking at closed system, so M has to be constant, right? There's no mass exchange. We're not changing the gas inside, so the gas constant. So basically isothermal. So I had the ideal gas law. Special case of a polytropic process. N equals 1 with an ideal gas that just breaks down to an isothermal process. Okay, so these are just introducing different processes and different expressions. We'll deal more with isentropic. We'll make some examples of these. We'll do problems with examples of all of these. So let's do more on boundary work. So we all drive cars, or we've all probably driven a car, and we have a piston type engine. Now we're getting electric cars, okay. But nevertheless, boundary work, piston, go from state 1 to state 2. I have some elemental area. I can break all this stuff down. Area under the process curve on a PV diagram. Represents the boundary work. Piston process path from 1 to 2. This represents, in this case, okay, it ends up being, for this argument, right, it's clockwise, so this represents work by the system. So, boundary work during a process depends on the path. So I can take path A. I can take path B. Or I can take path C from 1 to 2. And the area under the curve changes for each one, so I have different process, right? So I have different areas under the curves, right? So boundary work in a process depends both on the path followed and the initial and final states. So if I make state 1 here instead of there, and I take path B, I have a different area, right? So it's just initial and final states dictated by the initial kind of boundary conditions, right? So also the net work done during a cycle is the difference between the work by the system and the net work done and the work done on the system. So if I'm counterclockwise, I have more work done on the system than by the system. So in here I have this clockwise work by net, counterclockwise work on. So more on cycles. So again, cycles with no mass flow across the system boundary. Closed system. Just gonna put here delta E equals, okay? And then 4 closed system. So let's go back up to here and let's say we have state 1, so I have some V1, state 2, so I have some P1, P2, V2, V1, and I have a path 1 to 2, and I have a path 2 to 1. I have a counterclockwise, so area work done on the system. Now the question is, so I have a cycle. I go from one state to another state and then back again. In this case, my paths are not identical there and back. It ends up being counterclockwise, so it ends up being the net work done on the system. If I had to move the clock hands back, right, I had to do work on the system, on the clock. Okay, what is delta E? What is the change in energy for a cycle? I'll put internal here just for clarification. So what is the change in internal energy for a cycle? Closed system. No, just what? Okay, so we could write out the first law. Okay, we could do that. Yeah. So let's just look here and think about this is state 1. How do we define it? Right? If I'm saying this is a state, it's defined by the temperature and pressure. So if this is a state, the temperature, there's a T1. If I go a cycle, I go right back to the same temperature and pressure, closed system, I didn't add any new mass. And if I'm at the same temperature and pressure, the internal energy is right back to where it was. Now, if I have an open system, so then I just want you guys to think about that. And I'm just going to write only question mark equals 0. So for a cycle, if I have an open system, what happens?
Can change.
If you're still going back to state 1, it's still 0.
Yes. You might have a different mass inside, but you're right back to that same internal energy. So typically, it depends on whether it's big V's or small V's, or it's kind of coupled to this. But in general, you're going to a cycle, you're right back to where you were. You can have mass leaving and then mass back, but you're at state 1. State 1 has a temperature and pressure in a given mass. Right? State 1 has a given mass associated with it, a given temperature, a given pressure, a given volume. Now, it just turns out that all you really need is the temperature and pressure to define the internal energy. So if it's an open system, you have mass coming in and mass coming out, but once you get back to here, you have the same amount of mass as what you had before. So, any cycle, you get back to your initial state. If you change the mass inside, you're no longer at that initial state. You might be at the same temperature and pressure with a different mass, right? But it's not exactly, I mean, really all you need is temperature and pressure, but, you know, really you have a different amount of mass. Now, if you do it on a per unit mass basis, then it doesn't matter for sure, right? For the internal. So these are just some notes on clockwise, counterclockwise. I've talked about this I don't know how many times. Work net equals work by. This is boundary work. PV diagram. Counterclockwise work net equals work on. Boundary work PV diagram here. That's what we're. So first law, I can write out the first law. Q equals delta E minus W. So I could say Q in, because that's what Q represents here. Delta E, I'll put the internal here. Or I could put system. And then this is the work on the system. The surroundings, Q is the heat input, right, from the surroundings. So this is the compact way of writing it, right, the first law. So let's just expand it in red from an energy balance standpoint, right? So I have Q in plus work in plus the energy associated with mass in, and we're just going to say that's 0 because we're dealing with closed systems, minus Q out plus work out plus the energy associated with mass out, and again that's 0 because we're dealing with a closed system, equals delta E internal, or the change in energy in my system. So I could put subscript system, I could put just a big U here, but I have this, so written in the first law format in order, so I have that. I need a minus sign over here, so it's a net, so if I'm going to make a minus sign over there, right, it has to be net work in, and in order for this to be positive on this side, right, I have to have a net heat in. So there's an amount of heat in and there's an amount of heat out, but if there's more heat in than heat out, then it's really a net heat in. So you can just write out this full energy balance form and then get right to here where I get the subscripts in and on. So we'll pick up here after next lecture.